I'd like to revisit partial and semi-partial correlations because this is an essential element for understanding the next topic. And in order to explain it a little bit better, I want to borrow from a graphic, but a graphic that's different than Cohen and Cohen. So to begin with, we start out with Cohen and Cohen, and you can see that Cohen and Cohen, they do, or it's Cohen and Cohen West and Aiken, but I just refer to it as CC. They define the partial correlation, or partial R, which is a little bit misleading. It's really the partial R squared and the semi-partial R squared, but they refer to those as portions from a Venn diagram. And those portions for a partial is A over A plus E, and for a semi-partial squared equals A. Now, in order to give a little bit more color commentary to this, I pulled this off the internet, and they use different letters, so I'm just going to refer to these letters rather than confuse you with different letters and trying to convert it back to Cohen and Cohen. So we have two predictors, x1 and x2 of y, and these circles are unit variances. So they're, imagine that they're just standardized variables, and each one has a diameter of 1. And the reason for it is these circles have to be identically sized in order for the overlap to make sense. Where they overlap and where they don't overlap are lettered A, B, C, and D. A right here is this portion, and it's the unique portion of y that isn't explained by x1 or x2. So this would be similar to 1 minus the r squared for a regression where x1 and x2 were to predict y. So this is our residual. And this is the residual variance, and it's the unique variance of y. B is the shared variance that is unique to x1 and y. And that is this weird shape right here. And B is common variance that would oftentimes be referred to as the coefficient of determination between x1 and y, provided that x2 were partialed out from y. So in other words, if you took y as your criterion and you used x2 as a predictor, and you save the residuals, the residual variance would be AB. It would be this weird shape with this bite taken out of it. So AB is the leftover variance after you take x2 out. And B then would be what would be accounted for by x1 should x1 be the predictor of the residual of y after x2 were a predictor. Similarly, D is the unique variance between x2 and y after x1 is taken out. So B and C are taken out by regressing, by doing a simple regression where y is a criterion and x1 is a predictor. B and C is the variance, the shared variance between x1 and y. You take that out. And if you use the residual as the criterion and use x2 as a predictor, what you would get is D. And D would be the common variance between x2 and y. Okay. C is a weird piece, and here's where multicollinearity comes in. C is this weird piece that's shared between x1 and x2 and y. And the real difficulty in statistics is that we don't know to what predictor do we attribute C. Do we attribute it to x1 or do we attribute it to x2? Or do we just ignore it because it's confounded between x1 and x2? So what I want to do is I want to revisit all of the partial and semi-partial definitions so that it's a little clearer what's happening. So if I refer to my figure, a partial correlation coefficient, and I'm going to square these because it only makes sense. A partial correlation is B over B plus A. So here we go. B over B plus A. So what is that saying? A partial correlation is telling us the proportion, because it is a proportion. It's a proportion of b over b plus a. So therefore, it's the amount of variance that's shared between x1 and y that's unique over the total amount of variance that's available to be able to be explained. So therefore, when you square the partial correlation coefficient, it's something that is directly interpretable because it tells us what part over what whole we are getting from our unique relationship between x1 and y. So do you see that? B over b plus a. Similarly, the partial correlation coefficient. Now remember, these are squared, just like when you want coefficient of determination, we need to square those. If we don't square them, then we get values that are correlations, and they're not interpretable. That's not a metric of shared variance. So the squared partial r for x2 is d over d plus a. So it's this part over this whole. Okay, so it tells us exactly what proportion this piece right here is of this whole thing that's unique of x1. Okay, now that's partial correlation coefficients. What happens when we're looking at the correlations themselves? Well, the correlations are pretty simple. That the correlation, and this is the coefficient of determination. The coefficient of determination is b plus c. So let's look at why that is. Well, it's b plus c. Now, why is it that we do not have to do our coefficient of determination b plus c over a plus b plus c plus d? Because that would make sense, right? And the reason for it is that this is a unit variance. And so we know that the total amount of variance here is 1. And therefore, b plus c, this shared variance, this overlap, is directly interpretable. Now note that when we get to the semi-partial correlations, that they're not directly interpretable. So, okay, so now the first coefficient of determination for x1 and y is b plus c. The coefficient of determination between x2 and y is c plus d. And that's what you'll see right here, c plus d. Okay, now let's shift over to semi-partial squared correlations. Well, if you look at the semi-partial correlations are the total amount of variance that's explained, okay? The total amount of variance that's explained by our regression model, minus the variance that's explained by the other variable. Okay, so what it gives us is, this is the r squared for our model, and this, if you recognize this, this is the coefficient of determination for x2. Note that this is for x1. This is the semi-partial for x1. And that leaves us with b. So what are we doing? Well, we're taking b, c, and d, and we're taking out c and d. So that gives us b. Now, why is the squared semi-partial correlation not directly interpretable? Well, we don't know what a is, and we don't know what c and d are, because they have all been taken out. So b alone is not directly interpretable, or it's very difficult to interpret. So we have to work backwards to try to figure out the residual variance, the unique variance that isn't accounted for. Also, we need to know what this squared correlation coefficient is, the coefficient of determination for this guy. And so that's why the squared semi-partial correlation is not directly interpretable, but it is an interesting piece because truly it is the unique shared variance between x1 and y and between x2 and y. So it's b and d. And you'll see that right here. It's just b and d. So those are the differences between partials and semi-partial correlations. And the reason why I wanted to go over that is because these are important building blocks for us to understand when we start moving into things like stepwise and hierarchical partitioning of the variance which is my next video. So stay tuned for that.